This is Physics 1101, Lecture 1. On Chapter 1. Alright, so I will be doing these lectures on each of the chapters. I'll be posting them, and then class will be mostly answering questions about it. Alright, so again, the book we're using is Giancoli Physics, 7th edition, and we started right from the beginning. So chapter 1 deals with measurement. All right, and the main thing is involved with this are units. And in this case, we're going to be using SI units, Standard International Units, metric system. We will be using English units, but only for points of comparison, because we're still more comfortable using English units for a lot of things, like miles per hour, pound force is pounds. Hardly any of us have any can relate to a Newton or a speed of meters per second. So we'll be doing that. I'll be converting that just for point of information. There'll be no questions related to metric units or conversion, but it's handy to know what some of these are as we get into this. Units, prefixes. We'll get into not much on prefixes. Let's see, we have conversion, and this would be only in the metric system. All right, and understand what kind of units we have for different systems. So in acceleration, it's meters per second squared. Velocity is meters per second, and that kind of stuff like that. We'll also get into significant figures. We'll have on every test, we'll have questions on significant figures. Some of these things will be also related to lab. I'll be dealing with this when we get that, significant figures in lab. How accurate is the number or measurements and stuff like that. Scientific notation. And so on. Okay, so this will be the basis of chapter 1. So I'll go over chapter 1 today. There's not a lot to it overall as far as that's concerned. So, all right, so I guess first thing is I'll deal with significant figures and accuracy and uncertainty, because that's how it's done in the textbook, and it has nothing to do with units. So suppose I have two numbers. All right, one is 10 meters, which is, say, the width of the room I'm in is roughly 10 meters across. I'm not going to do it, but the lab we're in, the classroom lecture is about 10 meters across. All right. So that measurement, and supposedly I was to measure it and get a number of 10.000 meters. All right. Is there a difference between these two numbers? As far as just pure math is concerned, nothing. This is 10 meters and that's 10 meters. But as far as the accuracy is concerned, all right, this 10 meters can be implied, basically, this could be anywhere between, roughly 9 to 11 meters. Anywhere in there. I could do that just from pacing off, knowing I have one step is about a yard. Well, step, so if I do a certain number of steps, it's going to be a certain number of meters, roughly. So that's that. This, on the other hand, is 10.00. So I'm measuring this to a thousandth of a meter, which we'll see is a millimeter. This implies an accuracy of 9.999 all the way up to 10.001, roughly, meters. So far more accurate. This would be 10 meters. We actually want to express it in terms of uncertainty, plus or minus 1 meter, which is about 10%, which is probably roughly what it would be if you were just to measure it based on pacing off. This, on the other hand, implies 10.000 meters plus or minus 0.001 meters, which is an accuracy of 0.01%, roughly. Right? 1,000 times better. 10,000 times better. So this would be actually, that's even 0.01%, 1 part. Yeah, that's about right. All right, so that's what we have there. So these are measurement, significant figures. So if you look at this number has one significant figure. I'm going to use SF for that. This number has 1, 2, 3, 4, 5 significant figures. It is 5 times more accurate as far as the accuracy of it. So when you have zeros afterwards, the accuracy implies that. So let's do another example of some more numbers. Say I have 5.02 meters and 5.0200 meters. All right, what would be the significant figures of each one? All right, well, this one would be 1, 2, 3. This would have 3 significant figures. This one have 1, 2, 3, 4, 5. 5 significant figures. So that's the accuracy there. So trailing zeros after that implies that, right? So generally it's from the first digit to the last digit is the number of significant figures. All right, so that's the start there. Okay, so let's move on a little bit here. So if you have some other numbers, so you gotta be careful. So again, 5.20200 is 5. All right, what if you have a number that's very small? 0. Let's add a 1 to this. So a 1 to this would be 5.0200. 1, 2, 3, 4, 5, 6. This is 6 significant figures. All right, because this implies a length of 5 meters to an accuracy of 1/10,000th of a meter. Suppose I have number 0.00001, all right? Lots of digits here. You might think, oh, how accurate is this? Well, this would only have one significant figure. That's because this is, even though the accuracy for both of these is in the 10,000th, or let's see, 1,000th of a millimeter, this number is itself 100th of a millimeter. So this one, we have a length of 5 meters with an accuracy of smaller than, you couldn't even see it, smaller than a hair. This, on the other hand, is basically a hair sample, the thickness of a hair to the accuracy of the thickness of a hair, which is quite a bit. So you got to be careful there. So again, leading zeros in front, or if you have numbers after like this, like 502,000, this only has 3 significant figures. So that's the point of significant figures there. So we can write this better, a better way of doing it, like this number here, each one of these. So if we write these in scientific notation, the first one would be 5.02001 times 10 to the 0, right? Because that's 10. This number would be 1, 2, 3, 4, 5. 1 times 10 to the minus 5th meters, right? So the number of significant figures is in the number before the exponent. For here, this would be 5.02, and that'd be 1, 2, 3, 4, 5 times 10 to the 5th. So this would have 3, this would have 1, and this would have 6. So when you convert it to scientific notation or powers of 10, and the way to do it is you go from this point 1, 2, 3, 4, 5 to get to there. That's 10 to the minus 6, going that way. This one we started here, go 1, 2, 3, 4, 5. That gets us 5.02 times that 5th. So going that way, we have positive exponent. You go that way, you have a negative exponent. So that's accuracy and significant figures. And we'll be dealing with this a lot when we deal with labs, like how accurate is a lab measurement that you're doing? Is it very precise? Or are we doing it like, are we doing something with a micrometer? Or are we doing something we're just doing with a ruler to measure? Are we timing with just a stopwatch? Or are we timing with a high precision system, which we have here sometimes? So that's kind of what we're looking at here, is how accurate are your measurements? All right, so next thing are the units. All right, again, we're using the SI units, metric units, and these are meter, kilogram, second. Now there's other units we'll be using, but these are the primary ones. All right, so a meter, unit of length, unit of mass, unit of time. Those are our fundamental ones. We're not going to get into the precision of that, but we can see how accurate things are. So if we look at the meter is actually defined in the time speed of light, and it turns out the meter is defined, the speed of light is 299,792,458 meters per second. So that's how far it travels out. So the second is actually defined as 1 second is defined as the length of time, for a beam of light to travel 1 meter. All right. Yeah, length of time. So we define the meter. This is V, and we'll get into this. Velocity, as we'll see, is distance over time. So distance is time times velocity. So this will be the distance it travels in 1 over this second. So if you take 1 over this, that will be how far, that's how far 1 meter is. So this is actually defined to 9 significant figures. All right, we're not going to get into it. But the meter is defined to 9 significant figures. The second is defined, so meter is defined with that. The second in time is defined by the oscillation of the cesium clock and it's known to 10 significant figures. Most standard units you use are this accurate. We need to be this, because we have GPS, all right, GPS satellites. They measure things within a few centimeters, all right, over vast distances. You need things to 9, 10 significant figures if you're going to have clocks, GPS, and systems that are this accurate. And that's the whole point there. Okay. What else? Okay. So that's it there. I'm not gonna do questions on, what's the speed of light, but that's approximately what it is. Again, for when we see later on, we're gonna use speed of light as 3 times 10 to the 8th meters per second, and we're using the unit C for that, letter C for that. But we'll do that later on. So this is the speed of light, and approximately it's that. But this is how it is precisely. All right, now prefixes. All right, so I will have questions on tests that I have. We'll just use units, and you gotta make sure you pay attention to that. So starting from the smallest one, biggest one we have giga. All right, gigameter. Giga is 10 to the 9th. Might as well have tera. Tera is 10 to the 12th. Then we have mega. So these are all capital letters, which is 10 to the 6th meters. Then kilometer, first one, it uses the smaller, is 10 to the 3rd. We're not going to be using anything else. So then those are the ones we'll generally be using that are larger than 1. Notice they're all multiples of 3. All right, go to the other end, we have a centimeter, which is 10 to the -2nd. We have millimeter, which is 10 to the -3rd. So the prefix is that. We have micro, so the Greek letter mu is 10 to the -6th. We have nanometer, the prefix is n, which is 10 to the -9th. And generally below, the picometer is the smallest we're going to be using for this class, is 10 to the -12th. Oh, that's 9, not 19th. All right, so those are the unit, the system, the prefixes we'll be using. They go from higher up and they go much farther down. That's fine. If you look at the Power of 10 video, Powers of 10 video and the quiz, they go from a huge range as far as that. So a nanometer is about the size of an atom. You get down to picometers, you get the size of the nucleus, a little bit more. A femtometer. So as we do, a femtometer is about the size of a nucleus, or size of a nucleus 10 to the -15th. So notice these are all, except for centa, are all multiples, negative multiples of 3. Okay. All right, so that's it there. So again, in tests, I may just have a problem. It has 5 nanometers. All right, you need to know that this is 5 times 10 to the -9th meters if you're going to do a problem. Because when you do actual problems, you need to convert back to millikilogram and seconds. All right. Meter, kilogram, seconds. So if you have a problem with that, you want to get an actual answer, you need to make sure you convert it back to the units. So that's it for prefixes. So, right? Actually, we're getting about near the end here. And yeah, a little bit here. The last part gets into the idea of what we call dimensional analysis, right? And this will be very important if you're doing a problem, to make sure units are consistent. All right, if we add, say, 5 plus 4, we get 9. Okay, so what? All right? All right, so that's just a math problem. However, if we're doing problems in physics, all right, if there's no units to it, then it doesn't matter. If you just have 4 plus 5, you get 9, right? But if you have 5 apples plus 4 apples, 4 oranges, I mean, what do you have? You don't have 9 apple oranges. You have 9 of these things. We're just counting. But these are different units. This is apples and these are oranges. So you don't end up with just 9 apples. So this will be the same thing we'll see in physics, is you have, when you're adding terms, they all have to be the same units. So let's get into a little bit this here. So we're going to have a problem, and I'll just use what they got in the book, is V is V naught plus 1/2 AT squared, and X is V naught times T. Okay, this will be part of chapter 2. So we'll be doing this, but stressing this, we're not going to get into the problem units, but each of these are in units. V is a unit that has meters per second. Acceleration has units of meters per second squared. All right, so V naught means initial. So if we're much like if we're going to add 5 apples plus 4 apples to get 9 apples, we have to add all these be the same, otherwise it's kind of meaningless. Like, what would be if I had 5 meters plus 3 meters per second? What does that mean? That's kind of a meaningless thing. You're adding a distance to a speed. This is nonsense. So they have to be all the same unit. Meaning if we have 5 meters plus 8 meters, we get 13 meters. If we get 5 meters per second of speed plus 3 meters per second, we get 8 meters per second of speed, velocity, as we'll see. Okay? So we add that. So in this case, let's start with the simple one here. X is in units of meters. So this would be units of meters. And V is meters per second times time. Time is units of seconds. So this would be that. This unit would cancel with that, and we're left with just meters. So this formula is correct. I mean, that's one way of keeping track. If I had X is trying to keep track of it, V naught over T, then this would be meters. This would be meters per second over second, which would be meters per second squared, which is not the same as that. So this is not the formula for X is V naught. It's X is V naught times T because the units work out on both sides. All right? Last one here would be this problem. So using this one, and I'll do it above. All right, so this is units of meters per second. This is in units of meters per second. All right, acceleration is meters per second squared times time squared. And wait a minute. Oh, yeah. And you'll realize this is not correct, because this would be units of meters. So this number, this formula is not correct. I can tell that just from the dimensions. These do not add up right. What would actually be correct, because we'll see this for free fall, this would be X is V naught times T plus 1/2 AT squared, because this is in units of meters. So we gotta multiply this by that, so this would be meters. This would be meters per second times time, times seconds. And this we've already seen is meters. So this is the correct expression. All right, this looks fine, but it's wrong because the units don't match up. So this is how you can make sure your formula's down right, is to check that the units of each term are correct. So that's chapter 1 as far as that's concerned. This will be very important when we have other formula stuff, because it's very common to write a problem down wrong. All right, do something where v, x is 1/2 AT. Thinking, well, that sounds right? And that's not right at all. Okay, so